Thank you everyone for coming. Today it's my pleasure to introduce Allison Chaney, who's a postdoctoral fellow at Princeton University, and is currently working with Barbara Engelhardt and Brandon Stewart, and she received a PhD in computer science at Princeton under David Bly, and has a number of other degrees. And I'm very excited to hear her talk about the social side of recommendation systems, how groups shape our decisions. So let's welcome Allison.
Thank you. So as David said, today we're going to be talking about how groups and social influence shape our decisions, specifically in the context of recommendation systems. All right, but first I want to talk about my broader research agenda, which is about influencing deliberation, or how people think about things. And there are two main branches. The first branch is making tools for knowledge creation. So how can we make it easier for domain experts to create knowledge in their fields? And the second branch is about understanding decision processes, or how do people decide what choices they're making. And these two branches are related to each other because it requires knowledge to make decisions, right? It's the foundation of decision making. But at the same time, you're making decisions in the process of creating knowledge, right? So these two branches interact with each other. And primarily we're going to be focusing on this second branch today, but I wanted to start by giving you a glimpse of what I do in this first branch. So for tools for knowledge creation, right now there's this rising tide of data analysis and data science. People are really interested in applying machine learning models across lots of domains. And so I've done this, and I'll continue to do this. And I just want to highlight two things about my work. One is that I focus primarily on unsupervised machine learning methods. And that's different than a lot of the supervised machine learning, such as deep learning, that's really popular right now. And the main distinction between unsupervised learning and supervised learning is that supervised learning is more geared towards prediction. You want to predict something. You have an input and output, and that's the setup. Unsupervised machine learning is more about finding these patterns that perhaps are more interpretable. So it's about creating a more interpretable structure about the data generating process behind your data oftentimes. Okay, so again, I work primarily in unsupervised machine learning methods because they're more interpretable, especially to domain experts. All right, and then the other thing I wanted to highlight is that no matter how interpretable your machine learning methods are, you need tools for visualization or other tools to help domain experts really access those results. Right? Again, you can't just hand a historian a numerical distribution and expect them to really understand your machine learning model output. You need some sort of tool to help them translate and access those model results. So again, I've done that, and I'll give you a couple of concrete examples. So one thing I've done is build a tool for visualizing topic models. For those of you who aren't familiar with topic models, what they do is they take a collection of text documents and they break down the text and describe that text in terms of topics. Right? So you could have a topic that's about the government or the economy or literature, and these are all just the general themes in the collection of documents. And then for each document, it breaks down that document in terms of those themes. So you could say this document is for 50% about economics, 10% about statistics, et cetera, and you do that for each document. So that's what topic models do. So I built a tool to help domain experts, or just anybody really, to visualize the results of a topic model. Because again, it's just a statistical model output, and people need to be able to access these results. So I built a tool to do that. And one thing I wanted to note is that this tool and all of the other tools that I work on are or will be open source. And the reason I think that's important is it allows people to take what you make and make it better. So in this case, a lot of other people have taken the ideas from this work and built on it, and so now we have like LDA Viz, Topic Explorer, and a bunch of other tools that build on these concepts because I released this source code. Another thing I worked on is building a model to detect and characterize historical events. This was in collaboration with a historian at Columbia University, and here he had this collection of communications between different embassies. Sorry, I'm going to get my water real quick. Different embassies during the 1970s. And he just wanted to find what was interesting and novel in this collection of documents. All right. And so what we did is we built a topic model-based, machine learning model to help him do this. And one thing that he found that was interesting in terms of events that were new one event was that in 1973, the UN had a Security Council meeting in Panama. And this was exciting to him because he didn't realize that the UN had security meetings in Panama. And so that, again, he was just really excited about that. But aside from detecting events, the really cool thing I think about this model is that you're able to characterize events. So then for each event, you can say what words are related to this event, and then what primary source documents are related to this event. And again, this is super interesting relative to other work, which was all about just clustering documents together. Here we're about pulling out documents that are relevant, so then, say, a journalist could look at them and find primary source documents to support their work. Another thing I've worked on is a tool for aggregating topics together in this topic modeling context. So one problem is that social scientists want to use these topic models for measurement. They're interested in learning something about the world through these topic models and using the topic model to measure what's going on in the world. And these concepts are hard to measure often. So an example of this is Amy Catalinic is a political scientist, and she wanted to use a topic model to describe or to measure when there was some electoral reform in Japan. In this electoral reform, she argued that it caused a shift in terms of what the politicians were writing about and campaigning about from local governance to foreign governance. Okay. And so again, she wanted to use a topic model to help capture this concept. Now, the challenge when applying the topic models to measure concepts like this that are a little bit vague is how do you set K, right? How do you set the number of topics? So in a topic model, you just have to set some number of topics. Do you set 10 topics that you want to find, 100 topics? And it's a challenge for any social scientist or anyone who wants to apply these to their work. So what we're proposing is that instead of setting a small number of topics and trying different things, you set a very large number of topics, so like 1,000 topics, 2,000 topics, and then you aggregate those topics together, maintaining the same statistical properties of the underlying model, but now you have interpretable themes because you're using a combination of clustering, also combined with domain expertise. So they can say these two topics are kind of covering the same thing. This is the concept I want to measure, because measurement is inherently, you're imposing some of the domain expertise knowledge onto the model that you want to capture these concepts to measure. Okay. And the last thing I want to talk about here is generalized non-parametric deconvolution models. So this is current work with Barbara Engelhardt and a bunch of other people at Princeton. And here the idea is that you have a sample of cells, right? You have red blood cells, white blood cells, skin cells, etc. Lots of different cells. And in that cell sample, you want to be able to apply some sort of model. And again, you have like lots of different of these, so lots of different samples. You want to be able to apply a model to say, okay, well, what do red blood cells look like in general from these samples? And how many of them are in each of these samples, right? A typical factorization model can do something like this. But what's different about this model is we want to be able to say, okay, what do red blood cells look like in this particular sample? And how do they differ from the global distribution of red blood cells? Okay, and that allows us to discover disease or characterize disease. We also want to apply it to like political voting, so we can find out outlier voter districts when do Republicans look a little bit different than the usual Republican distribution. So that's this model. So again, a lot of domain experts want to apply tools to learn from their data. And so I've done this, and I want to continue to do this in my work. Now, switching gears, I want to talk about the other branch of my research. And this is what we're primarily going to be focusing on today. And this is understanding decision processes, or how do people decide what choices to make. And what do decisions look like in this context? Well, we're primarily going to be focusing on consumer choices. So buying things on Amazon, clicking on things on Facebook, searching for results using Google, clicking on news articles. So who here in this room has used one of these services in the past 24 hours? Yeah. People aren't raising your hands. I know. All right, so this is important. And these are important, especially in aggregate, right? You might say, well, it doesn't really matter what music I'm going to be listening to for the next 5 minutes. That's a trivial choice. But if you're making these decisions day after day, it can impact your happiness, your relationships with other people. It can impact economies and even political elections. So these choices are important in aggregate. Right? There are also hugely important decisions that are important individually, such as criminal profiling, loan approvals, and medical interventions. We're not going to talk about these today, but I'm hoping that some of the work that we're doing in these more trivial decisions, or the things that are only important really in aggregate, can then be used to inform the way that we're thinking about problems that are more important for each individual decision. Okay. So we're going to be talking about 3 pieces of work. The first is Chameleon Preferences, or how do the decisions people make change based on the people around them. I think you're right. Should I move to the other side? Okay. All right. The second thing, so now that we've established that people change their behavior, then we're going to leverage the fact that people are social to find better things to recommend for individuals. All right. And then we're going to leverage that by turning off my slides. Give me a second. All right. Right. Going forward. Okay. Then we're going to leverage that to understand the impact of these recommendation systems. So we will have established that recommendation systems can be built to influence people, and then we want to look into the impacts and how that impacts group behavior. All right. So let's start with the first one. How do the decisions people make depend on the people around them? And this is work with a lot of great folks at MSR, Microsoft Research. Okay. So the problem here is people's individual preferences. Let's just assume you know people's individual preferences. So you have person red, person blue. What does the group want to watch together? So maybe everyone hold up your hands in terms of fingers. What movie do you think they're going to want to watch? Movie 1, 2, or 3? Maybe 2, 3, 1. Okay, we have a good distribution. All right. So what you're choosing is encoding a different value system. Like whatever your choice, it's encoding a different value system. So here are some aggregation functions. One is average satisfaction. Right? That's going to be the people who held up 2. You want to average the 2 preferences. All right. Another is least misery. Right? That's going to be the third choice. You want to minimize misery. All right, and then another choice for the first movie is maximum satisfaction. You want to maximize individual happiness. Right? So these are 3 different aggregation measures. And we started this problem asking, well, which one is the right one? Which one should we use? Okay. And to address this problem, we had to look at some data. Okay, so the Nielsen panel, my guess is maybe 1 or 2 of you in this room might have been Nielsen panelists at some point. So the Nielsen panel collects consumer data from lots and lots of different people. I was a Nielsen panelist at some point after this project, actually. So we purchased some Nielsen data for a month because it had a large percentage of group views. So this had about a quarter number of group views. And group views here is defined as 2 people watching the same thing in the same household at the same time. Right, so technically they could be on different TVs, but we're saying that counts as group view. Okay. And this is different than all previous data sets or previous work that had been done and published, because previous work had looked at maybe 2% group views, because this data is hard to obtain. Right? So this is the first work looking at a large percentage of group views. All right. So just mining this data, what do we find? So I want to explain these plots. There are 5 discrete categories here. So there's individual male, individual female, all male group, all female group, and mixed gender group. And I don't want you to be confused about the lines, because again, they're discrete categories. The lines are just there to show trends between these categories to really emphasize those trends. Okay. So then what are we looking at here? Here we're saying that individual males spend about 10% of their TV views. They allocate about 10% of their views to sports events. That's how you do this. But all male groups allocate about 16% of their TV views to sports events. So what this is saying is that men watch sports more in groups than they do individually. Right? That's generally what this is saying. Right? And then we're also seeing things like women watch instruction and advice shows more individually than they do in groups, either mixed gender or single gender. Okay? So then again, this is important because this is what we want to model. We want to be able to capture this in whatever we're modeling. Okay? And we can look at a bunch of these. So another one is, guys, I keep doing this. All right, another one is news. News is something that you watch either individually or in mixed gender groups, but not in single gender groups. Feature films are the opposite. All right, and then we can do this for, instead of gender breakdowns, we can do age breakdowns. So adult and children, so people under 18 and over 18. All right, so here I'll highlight the sports events first. you see these interesting pulling effects, right? Where adults tend to watch things a lot, children don't really watch them, but then when children are with adults, they're going to watch something a lot more, right? So you can imagine for sports events, kids watch them with their parents, but they don't watch them alone. Right? Feature films are really interesting because they're not really watched as individual adults or children, but when they're combined, when children and adults are together, they're more likely to watch feature films. So it's kind of a family thing, right? But the reason this is particularly interesting is because going back to those average, min, and max, this is not going to be captured by an average, min, or max of these two endpoints here. Right? That's just not going to cut it. Right? So there are these subtle nonlinearities that we want to capture in this data. All right. So we looked at two-person mixed-gender adult groups. And we looked at this primarily because it was the hardest two-person group to model. So that the same results apply qualitatively to other group types, but I'm just going to show you this one. All right, two-person mixed-gender adult groups. We can look at the empirical distribution of these group views. So how do we read this plot? This is saying is that if a woman really likes a movie, and a man only kind of likes a movie, then they're still going to watch it anyway. Okay, that's what this is. It kind of goes the other way around. If a woman doesn't really like it, but a man really likes it, they're still going to watch it anyway. Okay. So that's how you read this plot. Is that the bottom is just the individual preferences, and then as you go up and down, that's the landscape of the group preferences. All right. And then we can show what the aggregation function will look like. So the average satisfaction looks like this. It's just this planar slice vector because you're just taking the mean of the two individual preferences. Maximum satisfaction does a little better. It has this nice V shape. Okay. Right, but we're still overpredicting this low area and this low preference area and overpredicting in both of these cases in the high preference area. Right, so we're overpredicting in some weird places. All right, so we think we can do better than this. So what we did is we fit a simple logistic regression model to model the probability of a group view, give it a bunch of stuff. So we modeled the individual preferences using Matchbox, which is kind of a matrix factorization type model, which if you don't know what that is, I'm going to describe it a little bit more later. So we have these modeled individual views for male and female, and then we have an intercept term, linear terms on each of those individual preferences, as well as quadratic and cubic terms on the individual preferences. And then with only a single interaction term between those two preferences, we get a much better model. Okay, we get this beautiful empirical landscape that shows these interactions. And the reason we chose that model wasn't for any sort of interpretability reasons. It was just the simplest thing that we could do that captures the landscape significantly better than anything else. Okay? And if these plots aren't compelling, we did do some held out AUC, and our model did better on that anyway. Okay. So the take-home message here, how do decisions people make depend on the people around them? Well, there are subtle nonlinearities, and so what this is saying is that social influence has complex effects on the way people express their preferences. Right? It's not just, oh, I watched something with you, and therefore we're going to average our preferences. Social influence has very complex effects. Okay. And viewing habits shift substantially between individual and group contexts. But then there's also this thing, which is that groups display markedly different preferences depending on their demographics. And this is dangerous because it's very tempting to use demographic information in modeling, but then you can introduce these biases based on demographic information. Luckily, our model was robust to that because we were modeling individual behavior and then only using demographic information to, group out different kinds of groups. But this is something you have to be very careful of because you can easily say, well, men like one thing, therefore we shouldn't recommend it to women, and then people get upset about that. Are you okay? She's good. All right. So now that we've established that people are social and they make decisions based on that social influence, how can we use that to leverage the social behavior to find better things to recommend for individuals? All right. So that's what we're going to do now. And then this work was with David Bly and Tina Lassie-Rod. Okay. So the typical recommendation system problem that most people have seen is I have a bunch of items that I like. What is the next item that I'm going to want to read, watch, consume? Okay. And the way that this is typically done, or not typically, one way this is commonly done is matrix factorization. So you frame your data in this sparse matrix of users by items, and then the ratings or clicks or whatever else that you're trying to capture are the cells in this matrix. And you want to approximate this with the multiplication of two low-rank matrices. And this is nice because then you can interpret these two matrices as latent user preferences and latent item attributes. So one thing you can do is say, okay, for one individual component K, just like topic models, you have to set the number of K, the number of themes that you're finding here. So for one individual K, you can say, well, okay, I'm seeing a bunch of items that are horror films pop up here. So let's interpret this K as the horror film topic. That's the theme that's being found. And then when users have high values in that same component, you can say, well, these users like horror films, right? And so then you can have this nice interpretation here. Okay. So one thing we wanted to do was include social networks into this paradigm, right? And the reason we want to do that is because if you think about it, what is the way that we got recommendations before algorithms? It was talking to people. We would ask for advice. And we'd most often ask for advice from our friends. So incorporating social networks is a very natural thing to do to get better results. Lots of other people have done this. They've tried to include social networks in recommendation systems. But I didn't like any of these, and I'll tell you why. The reason being is that all of these put individual users in some preference space, just like in matrix factorization. Then they added the social network, and then they used the social network to push individual users closer together in preference space. So if we were connected, we're assumed to have preferences that were more similar in this preference space. The reason I didn't like this is that I thought that instead of pushing individual users closer together in preference space, you should be able to do things like this. So say I'm connected to someone, and they like a particular item. Then I am more likely to like that exact same item because we're connected. Because I don't, like horror films because my friend likes horror films. I'll watch that particular horror movie because he watched it. Right? That's the concept I want to capture in my model. And these two concepts aren't totally, well, the two concepts are distinct, but they can be used in conjunction with each other, right? You can use a model that does both. But this second one is the one we're going to be showing you. All right, so let's look at an example Etsy user because I worked with some data from Etsy. All right, so let's call her Betty. Betty likes a bunch of items, and we use matrix factorization to model what she might like. And given that she likes a metal bracelet and a mug, let's say she likes these two components in matrix factorization, the metal bracelet's components and the mug's component. All right, but we also know that Betty has some friends, and those friends like some things too. So given this new information, we see that her friends both like this exact same metal bracelet. So maybe we don't think that she has a general preference for metal bracelets. Maybe we think that she just likes that because of her friends. So we'll remove that from her general preferences. Okay, so now we want to make recommendations for her. How do we recommend items? Well, we recommend a scarf because her two friends like it. And then we can recommend a lot of other things because either her friends like it or because of her general preference for mugs. Right? And this is an actual user that we looked at in our data set. And it turns out that the three items she liked the most were ones that, these are in the held out set. These were ones that were modeled by her friends instead of her general preferences. Right? Okay, so let's make an actual model that captures this. All right, this is matrix factorization. Here, this is graphical model notation if you're not familiar. Here we're saying these theta are user preferences. So for each user U, so we have U users, that's the plate replicate denotes replication, so U users. And each theta U is a k-dimensional vector of that user's preferences in, again, this k-dimensional space. Okay. Similarly, we have our item attributes. So we have capital I items. And then each beta I is a k-dimensional vector that represents that item in k-dimensional space. Yeah. Okay, so these are the rows and columns in our matrices. Right. And then our observed ratings, they're shaded because they're observed. We are imagining that they have possible dependence on both these item attributes and these user preferences. Okay, so again, this is just matrix factorization. Now what we're going to do is we're going to build on that and say, we want to include some notion of user influence. So now for each friend I have some sort of influence value that I'm going to be learning. So how much each of my friends influences me. And we're going to add that in as a contributing factor to our ratings in conjunction with our friends' ratings. So if my friend rates an item very highly, that's going to be weighted by the social influence, and I'm going to probably like it more. But if they don't like it very much, then that's not going to contribute a lot to my own preference. All right. As a generative model, we're saying that the ratings of user U on item I, given all of the other ratings in your data, is drawn from a Poisson distribution with two different components. And for those of you that care, we're just assuming gamma priors on all of the other latent variables. Okay. If this doesn't make sense to you, let's frame it in terms of matrix factorization again. So this first part is just general matrix factorization, saying user preferences multiplied by item attributes. And the second component is another kind of factorization. It's the social influence or user influence times the ratings matrix itself, right? Of this is all the other ratings. Okay, so it's two kinds of factorization in one. Right. Then the challenge here is that none of these values are actually known, right? The user preferences, item attributes, and the user influence are latent. We're assuming that they exist, but we need to learn them. Okay. From a probabilistic perspective, we are interested in the posterior distribution. And what this is the probability of the latent model parameters given the observed data and some hyperparameters. And this is just the posterior using Bayes' rule. So we have the joint distribution on the top, that's easy to compute. And then we have this intractable distribution down here. And it's intractable because you have to integrate over every possible setting of every latent variable that you have. And if you have a lot of users, a lot of items, that's going to just be intractable. Okay. So my approach to solving this is using variational inference. So we have our intractable posterior P, and we want to approximate it with some easy-to-compute approximation Q. And then we want to get Q as close as possible to P in terms of KL divergence, or Kullback-Leibler divergence. There we go. Okay. But if you're paying attention, you'll know that you can't actually do that because we still don't know P. Okay? The trick then is that we can do it in terms of the expectation lower bound, which is equivalent up to a constant. So there's some math magic there. All right. So that's the core idea behind variational inference. A couple of quick details is that this is what I showed you before, the Poisson distribution, that we're assuming our ratings are drawn from this Poisson distribution. What we have down here is equivalent to what we have above. And that's because the Poisson has this nice additive property. So then we can have two different auxiliary parameters, Z. To just break down, this is the matrix factorization part, the typical matrix factorization or general preferences. And then this is the trust factorization or the social factorization part. Right, and so that's just these two terms broken out into two Poisson distributions. And then we can just add them together because that's a property of the Poisson distribution. And we get this nice property. Okay. These are complete conditional distributions because of the nice conjugate relationship between the gammas and the Poissons. We can write out analytically the the complete conditional distributions. And the idea here is that now we can approximate theta using our current estimates of all the other latent variables. So we can take the expectation of the latent variables, plug that in, and now we have an estimate of what theta looks like. And then we can do that for the next one. Now with our new updated estimate of theta, we can use this distribution to compute what we think beta looks like, and then use our new theta and beta to compute tau, etc. We also have a distribution for Z, but I didn't show that here. So then this is a coordinate ascent algorithm where we optimize one and iterate through each of them. Okay, a couple of quick notes on inference before we move on. One is that unlike Gaussian matrix factorization, we don't need to sample zeros in this context. And this is really important. Matrix factorization is usually done with Gaussian distributions. And the issue with Gaussian distributions is that you have your data of what items you like, but then you also have to sample some zeros, so what items you don't like, right? And you need that in order to have some sort of inference that actually works to get real results. The Poisson distribution, the zeros are all implicit, which is really nice. So you don't need to sample zeros. influence, and so you can get some results without doing any sampling in that sense. And again, this is nice because how you sample the zeros, how many you sample, and how you weight them in terms of including them in inference, all impact your results. And so again, we're saying we don't need that. Like that's not an issue. We can ignore that. Okay. Another thing, which is true for both Gaussian and Poisson, is that you need some noise in your initialization. Otherwise, your components don't separate nicely. And then in order to scale this up to millions and millions of users, you're sampling your data to get stochastic updates. And because of this property of the no need to sample zeros, you need to sample entire rows to do these stochastic updates. Otherwise, this zero sampling property doesn't work. So you just have to sample whole rows instead of individual user item pairs.
So
okay.
In doing that, you bring along all of that particular user's friends.
So it's always given that the user's friends. It's a conditional model. So you're sampling, you're updating this user's preferences given all the other the friends of that user. Yeah. So I guess
so they
yes.
would all be.
Yeah.
Do you avoid this kind of network subsampling problem?
Yeah. Yep. Okay. Great. Okay. Then to do recommendation, we use expectations. So we can take the expectation of each term within, again, this was the parameter for the Poisson distribution. So then we can compute the expectation of the ratings of user use preference for item I. And then we can use that to say, okay, well, this is how much we think this user is going to like this item. Okay, this is filling in the cells in the matrix. Yeah.
So if you're mainly going to use this, what good is variational days versus just doing kind of math estimation?
So I think that the answer is a little bit nuanced because I think we do want, we do want some estimate. This is just for predicting the ratings, and there are other things you can be using the model for. So I think you can. I think one thing we're interested in learning, which I don't talk about in this talk, is the distribution of user influence. And so just having the maximum value isn't necessarily what you want. You want that whole spread. Yeah.
Question about the exchangeability. So it seems like you have this assumption of exchangeability across the people in the network. And I'm wondering if you've thought about there may be certain people in the network who are more susceptible to influence. Like in my house, I'm Santa Claus, so I'll buy for everyone. Maybe more people than someone else in the household might buy for. So can the model be extended to take into account that maybe some people will never buy toys, even though there are children in the network, while other people are going to buy for everybody?
Right. So I think the model includes that already in some sense, because it's modeling the behavior that we currently have.
So that's coming in as your preference then?
Right, as your preference. I think there are some nuances about buying things for other people, and that's a whole sub thing within recommendation systems. Because if I'm buying, pool cleaner and pink backpacks, that says something about me. Am I buying that pink backpack for myself, or am I buying the pool cleaner because I have a pool? And so there are interesting things about recommendation systems that kind of go beyond what we're talking about. But yeah.
So I'm kind of curious. You can only be positively influenced by your friends here,
Yes.
right? Have you validated that assumption at all? Because it seems like you might sometimes have negative influence if you don't like someone.
Mm-hmm. I think yes, you might want to do that. I haven't validated it, but I think that's a worthwhile thing to do. Absolutely. Yeah. Right.
That'd be hard to do within this framework, I guess, because you have this Poisson gamma thing, and so everything's sort of positive. It might be hard to put a minus, and then you have all sorts of messy things.
Yeah, you do. I think more so you want to just, you almost want to interact with users directly with some sort of experiment to just see if, providing the items, with this term, without that term, could, influence people positively or negatively and change their behavior. I think that in order to really validate it, you need to do some user experiments. Yeah. So one thing I did want to say here is that what this does is give you a rating prediction approach to recommendations, which I actually fundamentally disagree with. We don't care whether or not I would rate a movie 4.5 stars or not. What I care about is whether or not I would watch that movie relative to the set of other movies that I would want to watch. And so what I'm going to do is I'm going to use this to rank the movies or items, and then provide recommendation based on this ranking approach. All right. So in terms of evaluation, we did something pretty typical. We take a set of items, we split it into a training set and a test set, and then we make predictions for all items that aren't in the training set, including the items that are in the test set. So items in the test set that are higher up in this ranked list, that's what we want. We want the items to be at the very top. And so then, if the items are higher up, that's better. Specifically, the metric we use is normalized cumulative reciprocal rank, NCRR, and that's just 1 over the rank of the item that's being recommended for all of the held out items. So then, in terms of data sets, we looked at a bunch of different data sets. The first 4 are publicly available online at this librec.net website. The bottom 2 were kind of specific to us. So Social Reader was my collaborator had access to a popular platform, which needs to remain anonymous. And then I had access to Etsy data from the collaborator there. Right, but the thing I want to note is that the percent ratings and percent edges are all very low. So the percent ratings is just the user by item matrix. It's very sparse. Percent edges is the user by user matrix. And again, that's very sparse as well. All right. So now I can show you the very pretty figure that everyone wants to see, which is we do better than everything. Yay. All right. So ours is the dark green method, but the light green method is also ours. It's the social only version of the model without the general preferences, and that does pretty well as well. So we, one of those 2 beats everything. All the other comparison methods. Okay. Yep. Yeah, so those were the ones I showed on the earlier slide, that whole list of items here. I can share the slides with you if you want afterwards. Okay. So how did we leverage social behavior in order to make, recommend better things to people? What we did is we inferred how much friends exert social influence on each other, and then we incorporated that in making recommendations. Okay. So now that we've established that we can build recommendation systems that maybe change behavior, we want to look at the impact of that behavior. How do recommendations alter behavior, specifically in a group context? All right, so this is current work with Barbara Engelhardt and Brandon Stewart, and we have a preprint up on the archive, if anyone's interested in looking at that. All right, so this starts by looking at that plot that I just showed you, right? So proud of this plot. But then I looked a little closer and I found some issues with it. So one thing that I thought was fishy was Etsy right here. So for the Etsy data, I saw that the social-only version of the model did better than the full version of the model. And that was suspicious to me because the full version is more expressive, right? It should be able to capture, everything that the social-only version should be able to capture. So that was interesting to me. So I looked at the Etsy website and tried to figure out what was going on. What I found is that at the time that the data was collected, it's not so much now, but this still exists, just not as prominently. But at the time the data was collected, very prominently displayed on the website was an activity to feed. All of the items that your friends were liking at the time. Right? So then all the items that my friends liked were showed up, which means that's the very first thing I see when I go to the website, which means that's what I'm going to be clicking on. And if you think about it, that's exactly the model that we had. So the model that we were trying, so the model that was influencing people was the same as the model that we had. So then this model was influencing the way users were behaving, and that's a problem, right? Because we're just saying that we're matching the model that exists on the system already, right? So that's not really saying anything about what people actually want, that's just saying something about what's already on the system. All right, so we have this feedback loop that's really interesting that we need to think more about in machine learning, which is that you have platforms that have some underlying machine learning model. They make recommendations for users, and then those users interact with those items, and those interactions are then incorporated into the model. And the model is updated, perhaps with this biased data, but it's not biased in the sense that it's biased racially or anything like that. It's biased in the sense that there's an algorithmic bias. We're biased towards the algorithm that's already in place, right? And we wanted to dig into what are the impacts of this, right? We have recommendation systems that are deployed. All of you raised your hands. You're interacting with these recommendation systems that have this feedback loop, right? So one of the ways that this impacts us is through filter bubbles, okay? So we're all kind of familiar with the notion of filter bubbles. It's been around for a while, but we haven't really done anything about it as a society. We all talk about how it's bad that we're separating into these bubbles and things like that. But one thing I wanted to talk about in terms of filter bubbles isn't necessarily about how people are separating in the bubbles, but it's what's happening within a given bubble, right? What I think might be happening is that within a given bubble, people are homogenizing. People are becoming more and more similar to those within their bubbles, let alone, distancing the bubbles from each other. Okay. So I think this is important. I think that recommendation systems have a role in this. So what I've been doing is trying to understand this. So what we started with is a simulation. We simulated users having preferences for items. So this is some notion of ground truth utility, how much utility a user is going to be getting from a given item. And we simulated it using a matrix factorization type framework. Okay, but oddly enough, matrix factorization didn't perform better in terms of our results. It didn't have any kind of edge. But that's the assumption we did. Okay, so we simulated a bunch of these different worlds with users interacting with items and exposing them to different recommendation systems. So we exposed any world to a bunch of different recommendation systems. And in this context, the user's true utility, we know that because we've simulated it, but the users don't know the full utility. They know some noisy approximation of it because if they knew the full utility, then they wouldn't need a recommendation system in the first place. Okay, so we expose users to different alternative realities, and we want to see what happens. Specifically, we want to measure the homogeneity between users. And we do that using the Jacquard index. So for any given user, we pair them with the most similar user in terms of recommendation system space. So in matrix factorization, that's going to be the closest in Euclidean distance for this k-dimensional space. For the social factorization, it's your most trusted friend. For popularity, it's just a random user. Okay? So we pair each user, and then we look at the sets of items those users have. And again, we compute the Jacquard index of those items. So that's the intersection of the union. All right. And then we looked at two cases. And here, towards the top, we have more homogeneous behavior, and towards the bottom, we have more diverse behavior. All right. So in the first case, what we did is we just exposed users to random items for 50 iterations. And then at iteration 50, we trained the recommendation system and let that run with a single training instance. And here what we see, one thing to know, is that we're comparing this to ideal utility. Ideal homogeneity. Excuse me. So what I mean by that is that, if you have a friend, there's an ideal amount that you have in common, right? If you're both behaving, perfectly, getting maximum utility out of the world, you will have a certain amount in common with your friends. And so that's the ideal setting. And we want to compare to that, right? If you're getting more in common than that, then that's going to be bad. Or, it's saying that you may not be getting your ideal utility, and you're exchanging that for homogeneity, okay? Okay, so what we're saying here is that with this single training case, things stay pretty close to the ideal utility, right? This is the change in Jacquard index from the ideal. Right. But in the second training case, or the second case, we run for 10 iterations, and then what we do is that we run for 10 iterations on just random recommendations, and then at iteration 10, you train a recommendation model, all right? And then at the next iteration, you train on the model plus your last iteration, so you're continuously training in each new iteration using all of the data you have up until that point. So that's really going through the feedback loop. You're including this algorithmically biased data in your training set. What we saw there is that we saw these huge spikes in homogeneity. People were getting much, much, much more similar to each other than they would in the ideal setting, except for the random one. Right, so then for all of these recommendation systems, you were getting this homogenizing effect. Right. So why do we need to solve this? Well, one, we need better evaluation for recommendation systems. Almost all the data sets that are used to evaluate recommendation systems come from platforms that already have recommendation systems on them. So the evaluations are going to be biased towards the algorithms that were used to generate the data, right? We need to understand the impacts on human behavior, right? We're using these every single day. How is that impacting what we're doing? And the last one is we need to design better systems to increase fairness and social welfare, because different people might be impacted differently by this. If you're less frequently using the system, you might be biased even more than somebody who's frequently using the system and may not be, seeing the impacts of this as much. Okay. So, how do recommendation systems alter group behavior? Well, they push groups of users to have more homogeneous behavior than they ideally have. Or at least this has been our hypothesis. We're currently working on user studies to kind of show this on real users instead of just the simulated setting. So it's work in progress, but I think it's a really exciting direction and a new way to think about recommendation systems. All right, so what did we do? We first talked about how the decisions people make depend on the people around them. And then we leveraged that knowledge that people are social to find better things to recommend for individuals. And then last week, we talked about how recommendation systems, as deployed in the real world, can alter behavior and how that might be problematic. Okay, so just zooming out, I'm still interested in both of these branches of research. So moving forward, what do I want to do? Well, I want to work with domain experts across domains to develop new unsupervised machine learning methods and build interactive visualizations, again, bridging the gap between the people using the models and the people building the models. On the other side, decision processes side, I want to identify the impacts of algorithmic confounding, right? So this is the last piece we were talking about. And I want to build more recommendation systems, specifically ones that are robust to these effects, where we can use biased data, but still have a good system. All right, and then I want to explore the issues of fairness, accountability, and transparency in machine learning as well. A little more concretely, what does that mean? I want to work on things like identifying propaganda, characterizing outlier voters, modeling user preferences over time, again, understanding this disproportionate impact. But I'm also really interested in education and healthcare recommendations, which kind of bridges these two gaps. Specifically, you need to work with domain experts, the same that you would for building tools for knowledge creation. Medical experts have lots of interesting text data. There's interesting things with wearable devices as well. And we want to be able to use that domain expertise, but then also build recommendation systems for people making education and healthcare choices, right? Like as they're wearing, using these wearables, what choices should they make in terms of their activity or their diet, etc. So I think there's some really interesting work, again, bringing in domain expertise and recommendation systems to the table and building out work there. Great. So thank you for your time. If you're interested in reading any of my papers or the code, you can visit my website, and I'm happy to entertain questions now.
If you know the particular kind of recommender system that was used in generating the data, can you kind of adjust for it? I mean, you have basically a probabilistic model based on this kind of network influence matrix factorization. Can you put selection bias on top of that to statistically adjust for it?
I think you can. At least that'll help, certainly. I think it also depends on whether or not you know that it's like a collaborative filtering thing, or if you know the exact model. That's going to change what you're doing, because you can do some weighting with the propensity score weighting type stuff if you know the exact model. But if you don't know the exact model, you have to fit a model to approximate that, and then what are you fitting that on? And it gets a little messy because then you're probably fitting it on the bias data, and it gets a little weird. But I think you can do things along those lines. It's just the degree to which you're going to be successful depends on how much you know about that system. Any other questions?
So I'm really curious. So I really like your last thing when you were looking at the feedback and what its influence was. And it's clear that you should correct for it, but how would you ever convince a company to actually change what they're doing to try to get rid of that problem?
So I think what you do to convince them is say that you're going to be losing out in the long term, right? That you're going to be recommending things that users want less in the long term. And so then you're going to get users that maybe taper off, they're not as interested, because at the end of the day, the companies care about their bottom line and about making money, which means getting things to people that they actually want, and not things that they don't want. And so a better recommendation system will get people what they actually want.
Any questions?
Yeah.
Earlier, you talked about how there's like an ideal series of things that people would want in that, like the system that you have will maybe like bind you against that ideal purchase. Does that mean you won't buy the items? Because if someone is like, essentially you have like these social pressures, like is it possible that like that the way the site is set up plus the social pressures could still get the person to buy the items? Even if they didn't like, even if say like the social pressure is like you should buy the item even though you don't really want it. And then further, I guess if you make users more homogeneous, is there the potential for that to be easier for companies if they can only produce one product and everybody got the same product? Like, could that work the other way?
Right. So to get at your first point, I think, so imagine that you want to read a book, right? Want to read a book. You don't know what you want to read. You could spend 10 hours finding the book that you want to read the most, or you could use a recommendation system and just pick something that's pretty good, right? So the cost there to actually like spending all the time researching what book you're going to like the most isn't worth, you know, the time. So it's not about whether or not you would like it or would not like it. It's how much you would like it, right? And so recommendation systems are getting people to consume things that they might like, just not as much as they would like other things. So again, this is kind of answering David's question before. It's like, if you're getting people to like, to read or watch or click buy the things that they might like even more, that's better for you, right? Because then they're going to come back to your platform. Okay. Then to your second point about how you might just need to produce one thing, that's actually one thing we want to explore. So currently you have things like Netflix producing special like movies or TV shows, or Amazon, right? They're building these tailor-made systems or tailor-made content for people based on their systems, right? So they can say, oh, well, you know, we're seeing that people really like this kind of thing. Let's make something for this component in the matrix factorization space. So I think we're already seeing that happen. And one thing we want to study is, well, what happens when you start introducing items like that? Are people going to behave even more homogeneously? And, you know, that there are some good things that can happen socially, right? If that happens, you have things in common with other people. But then there's the question of, well, are you just, you know, are some people benefiting a lot from that and other people benefiting not at all? Because you have limited resources, so you're probably going to be making things for like 1 or 2 components worth of people, but not the whole spectrum. So then the minority users aren't going to get as much content. And that, you know, minority in the sense of they're not using the system in the same way that the majority does.
Very complicated. Thank you.
Yeah, no, that's good. No problem. Cool. Are there other questions? I'm also happy to talk offline if people don't want to ask publicly.
Yeah.
No, oh, sorry.
Can you think of ways? So I'm thinking about this thing about homogeneity, and then trying to imagine like if they did start tailoring things to say 1 or 2 sectors of the demographic that's consuming their media, and then not within Netflix's control, but those populations all of a sudden underwent some sort of shift where that wasn't what they wanted anymore, and then almost like the worst case for Netflix would be entirely stop using Netflix because Netflix no longer has the content that they want.
Right.
Are you able to identify like those sorts of shifts within the model here, or I guess going back to David's point, that would almost be like a reason that companies themselves would be interested in not catering to that homogeneity, right?
Right. So I think that also gets back to the point that I made of future work that I want to do of modeling user preferences over time. I think time dynamics and how people's preferences change as, you know, they get older or, you know, they're just exposed to different content, I think is important. And how that plays a role in the homogenizing effect, I think. So currently the model really can't capture things like that, but I think that there's definitely avenues for research there. Yeah.
I guess if you could get some company to convince you to give them some proportion of the traffic, then you can kind of do some sort of active learning.
Yeah.
Considering different recommender systems. And
Absolutely.
kind of tackle these things a lot better.
Yeah. No, that's one thing I'd love to do. Yeah.
Have you considered or thought about how friends
Right. So that's sort of like propagation of information along the network. That's definitely something that's worth considering, but I haven't done that in this particular company. I know a lot of people have though, and I think it's really important, and that it could be incorporated as well in this sort of the flow of information. Yeah.
I guess you could just add a second order term.
Yeah, you can. And then I think you can add second, third order terms and just kind of see what's important. Yep. Mm-hmm.
Well, let's thank our speaker.
Right. Thank you all.
Thanks.